All right, everybody, Chapter 4, Section 5, Properties of Logarithms. All right, the first example says to simplify each logarithmic expression. The first expression they're asking you to simplify is log of 1. Okay, first of all, please notice that this is a common log. We know this is a common log because the base is not written. Remember, the base is a subscript down here. Whenever the base is not written, remember from earlier lessons that the base is then assumed to be 10, and therefore this is a common log. Base 10 logs are called common logs. Okay, cool. This is asking you for an exponent. Please don't forget that a logarithm is an exponent. A logarithm is an exponent. So this is asking you for the exponent to which we raise 10 to get 1. The exponent to which we raise 10 to get 1. In other words, my base is 10. I raise it to some power, right? I raise 10 to some power and then I get 1. So let me ask you this. What would you raise 10 to in order to get 1? If you answered 0, you are correct. So then the answer here is 0. 0 is the exponent to which you raise 10 to get 1. Log of 1 is 0. Log of 1 is 0. Cool. Let's look at another one. Now this one's interesting. This one says log base 5 of 5. Now again, please, I'm going to keep on repeating this until hopefully it just, you hear this maybe even in your sleep because I say it so often. A logarithm is an exponent. So here they're asking you, what do I raise the base of 5 to in order to get 5? Again, your base is 5. To which exponent do I raise 5 in order to get 5? So what would you say? If you said 1, you are correct. If you raise 5 to the first power, you will get 5. So log base 5 of 5 is 1. The book names this as a property. Notice that if your base is some number and your argument is that same number, if the base and the argument are the same, you're going to get 1. So like log base 3 of 3 is 1. Log base 8 of 8 is 1. Log base 4 of 4 is 1, right? If the base and the argument are the same, the exponent is 1. Earlier, for this example, if the argument is 1, the exponent's always going to be 0. So log base whatever of 1 is 0. So log base 10 of 1 is 0. Log base 7 of 1 is 0. Log base 15 of 1 is 0. If the argument is 1, the exponent's going to be 0. Cool, let's look at another example. Okay, next one. The natural log of e to the 4th power. The natural log of e to the 4th power. Do you know what kind of logarithm this is? This is a natural log. Remember, whenever they use ln, that means natural log. This is a natural log. You must understand that since there is no subscript down here, the subscript is the base, the base is e. Whenever they use natural log, that means it's log base e. So your base is e. I'm not pointing at this e, guys. I'm pointing at the invisible e down here that is not written. The base is understood to be e. Now, remember, a logarithm is an exponent. So they're asking you here, what do I raise the base to in order to get e to the 4th power? What would you raise e to in order to get e to the 4th? Well, if you raise e to the 4th power, you will get e to the 4th. So the exponent they're looking for is 4. Cool? So I could drive this home a little bit more here. Whenever you have natural log of e raised to some power, the answer is just that power. So in other words, if I had written the natural log of e to the 5th, the answer would have been 5. Natural log of e to the 7th power, the answer would have been 7. The natural log of e to the 9th power, the answer would have been 9, right? Good job. Let's look at another example. Now, before we go actually further to the next example, there's 2 things I want you to remember, okay, that we've already studied. This is your exponential function, right? And this is a logarithmic function, right? These two functions are inverses of each other. F and G are inverses. That implies two things. F composed with G, that is f of G of x, is x, and also the other direction, G of f of x, that's G composed with f, is also x, right? So if you compose the exponential and the logarithmic function together, you're just going to get your argument right back. This is your argument, you get your argument right back. This is your argument, you get your argument right back. Please keep this in mind for the next two examples. All right, here we go, guys. We have log base 7 of 7 to the power x. Now, here we go. You have a logarithm base 7 right here. A logarithm base 7. And then you have an exponential expression, also base 7. A logarithmic expression, base 7, and an exponential expression with base 7. These are inverses of each other. Log base 7, exponential base 7. And because they're inverses of each other, we know what we're going to get. You're going to get your argument right back. What is your argument in this example? X. So we know the answer is simply x. Why? Because logs and exponential expressions, logarithmic expressions, and log functions and exponential functions are inverses of each other. Cool. Let's look at another. Here we have 10 raised to the power of log of x plus 1. One thing I want you to keep in mind here is, you see the subscript? Yeah, neither do I. That means the subscript is not written right here. The subscript is the base of this logarithm, and because we don't see it, it's assumed to be 10. That's really important because here you have an exponential expression. You have base 10 raised to an exponent. All of this is an exponent. So this is an exponential expression with base 10, while up here you have a log expression, also base 10. Exponentials and logs are inverses of each other, right? So because they're inverses of each other, we know this, that when you compose one with the other, you're going to get your argument right back, right? You're going to get your argument right back. Now be careful. Your argument in this example is not just x, it's actually x plus 1. So we can say your final answer here is just going to be x plus 1. Right, that's your final answer. I guess I forgot to box my final answer in the previous problem there. All right, again, you simply get x plus 1 because exponentials and logarithms are inverses of each other. Now, the rest of this section zeroes in on or focuses on 3 different rules. The first of the 3 rules is called the product rule. Let me write it for you now. The product rule says log base b of x plus log base b of y can be rewritten as log base b of x times y. You can see this is a product, x times y. So you can always rewrite the sum of 2 logarithms as 1 logarithm, and you just multiply the arguments. X and y are the arguments, okay? Of course, the bases have to be the same, okay? The bases have to be the same. Look at this example. All right, use the product rule to rewrite each expression as single logarithms. So the first example, example 2, part A, is going to be the following. Log 3 plus log 5. These are common logs, by the way. Common logs because the base for each one of these is 10. All right, using the product rule, we can rewrite the sum of these 2 logarithms as 1 logarithm. All we have to do is multiply the arguments. So then, therefore, this will be equal to, right, log, just 1 log, and then multiply the arguments. 3 times 5. Cool? So then this is log of 15. Log 3 plus log 5 is equivalent to log 15. The next part is natural log of x plus the natural log of x minus 1. All right, we can use the product rule here to rewrite this as one logarithm only. And the product rule, you can hear it in the name. The word product means multiply. What we want to do is multiply the arguments. All right, like this. Cool. You're really, that's all it is, folks, is just rewriting a sum of logs as a single log. All right? Good. If you wanted to, if you really, really wanted to, you can distribute this x inside of here like that, but you don't have to. So you can leave it like that. Okay, example 3. Use the product rule again to rewrite the following expression as the sum of two logarithms. Here's the expression now. All right, cool. So you have log base 3 of x squared times the square root of x plus 2. Now, please keep in mind that we're actually going the opposite direction of the product rule now. Think of it. You only have one logarithm, and they want you to rewrite this as a sum of two logarithms. So this example, you're going from one log to two logs. Now, according to the product rule, we can break this apart, if you will, as log base 3 of the first factor plus, now that plus sign is really important. It's not minus or anything like that. It's plus log base 3, that is the number 3 there, log base 3 of the second factor. And that's it, folks. You've rewritten this expression as a sum of two logs. Remember to keep the same base, okay, the same base. So it's log base 3 of the first factor plus log base 3 of the second factor. Cool deal. Okay, the second rule is the quotient rule. Let me write that for you now. Okay, here it is. Log base b of x minus log base b of y is equal to log base b of x divided by y. The left-hand side looks, almost identical to the product rule, except instead of a plus sign, it's a minus sign. So the quotient rule says you can take these two logs, combine them to be just one logarithm, and you could hear it in the name. Quotient means divide, right? So you're going to take these two arguments, x and y, and you're going to divide them. Now, it's very important. X is the numerator, x is the first argument, the denominator is the second argument, and don't get these mixed up, right? The order does matter. All right, cool. Let's apply this rule. Okay, example 4, here we go. Use the quotient rule to rewrite each expression as single logarithms. All right, here's the first one. All right, the first one, log base 2 of x minus log base 2 of 3. Now, we can definitely use the quotient rule here because you have two different logs and it's a difference, right? So this is a difference right there. And the bases are the same. So according to the quotient rule, we can rewrite a difference of two logarithms with the same base as one log, and all you got to do is divide the argument. So using the quotient rule, this would be log base 2. So there's your one and only log. The first argument is your numerator. The second argument is your denominator. Okay, guys. It's that straightforward. That problem is done. Cool. Let's look at the next one. Okay, example 4, part B. You have log x minus log of x plus 2. Just a side note, these logarithms are common logs because the base is not written. The base must be 10. So these are logarithms whose base is 10, or that is to say, common logs. Okay, guys, we have a difference of logs, and they have the same base, so we can rewrite this as a single log using the quotient rule. The first argument is your numerator. The second argument is your denominator. And you did it. All right. Cool deal. All right. Let's go to example 5, shall we? Okay, example 5. Use the quotient rule to rewrite the expression as the sum of three logarithms. All right. Here's the expression. We have log base 4 of x times y all over z. We're going to kind of unravel this, if you will, all right? So we're going to rewrite this as a sum of three different logarithms. All right, here we go. The first thing I want us to do is to use the quotient rule to undo this division. Use the quotient rule to undo this division, okay? So the way that'll work is you'll have log base 4 of the numerator. Log base 4 of the numerator. I want to make sure that that this base right here is clear that it's 4. I'm going to make that a little neater. 4. Okay. Anyway, minus log base 4 of the denominator. Okay? So that was the quotient rule right there. Okay, that was the quotient rule. Right next to this, I'm going to write in parentheses, that was the quotient rule. Okay, quotient rule. All right, next. What I'm going to do next is I see a product right here. So I'm going to undo this product, x times y is a product, using the product rule. So I'm going to break this first logarithm into 2 logs, all right, into a sum of logs. So it'll be log base 4 of the first factor x plus log base 4 of the second factor y, and then, of course, just bring down log base 4 of z. What rule I used there was the product rule, okay? We're done. We did it. This is a sum of 3 logarithms. You know, I am saying sum, but this is a difference. But remember that any difference can be rewritten as the addition of the opposite. So don't let the fact that this is minus throw you off. You did do it. It's log base 4 of x plus log base 4 of y. And then I guess you could view this as plus minus log base 4 of z, or plus negative log base 4 of z, whatever. All right. Cool deal, everybody. We'll go to the last rule for this section, which is the power rule. The power rule says that if you are taking the logarithm, log base b, of an exponential expression like x to the power p, log base b of x to the power p, x to the power p is an exponential expression. The power rule says you can rewrite this as p times log base b of x. So basically, guys, the power can come down to the front. The power comes down to the front, okay? This is the power rule. Okay, guys, example 6. Apply the power rule to rewrite the following expressions, I guess, as an equivalent expression, all right? Here's the first one. We have log of 2 to the power x plus 1. So according to the power rule, this entire power, this entire exponent up here, could come down to the front to rewrite this as x plus 1 times log of 2. Now, we have to make sure to keep these parentheses around x plus 1 because the exponent is more than one term. So we want to make sure these parentheses are there. All right, cool, you did it. This is an equivalent expression. Let's go to the next one. Oops. All right, cool. That's the answer. Okay, guys, we have the natural log of the square root of 5. Now, allow me to read, just to make sure that we are very clear, that the square root of 5 is the same thing as 5 raised to the power of 1/2. So if you understand that, then you know that this square root really means there's an exponent of 1/2, right? So the power rule then, now being applied, will mean for 1/2, will allow for the 1/2 to come down to the front. So then this is 1/2 times the natural log of 5. And you did it. Okay, very good. Let's go to one more. Okay, here, I think we're going to go in the opposite direction of the power rule because notice that this 2 right here is already in the front. So if you go in the opposite direction, the power rule says you can move this power back up on top of x. In other words, this expression follows this form, the right-hand side of our rule, and we can make it look like the left-hand side. Notice the p can be put back up as a power of x, right? So this 2 can be put back up as a power of x. In other words, we can rewrite this as log base 4 of x squared. Okay? Cool. Let's go to example 7, guys. All right, example 7, there'll be 2 parts to this. rewrite each expression as a sum or difference of logarithms of a single quantity. All right, here comes the first one. Okay, we have the natural log of y squared over xz. Now, the first thing I'd like to draw your attention to is we can undo this fraction bar, this division. Now, think about division. I hope that makes your mind go to quotient. This is a quotient. So we can use the quotient rule to undo this division here, like so. We can say this is the natural log of the numerator minus the natural log of the denominator. Okay, that was the quotient rule. Now, I can use two rules at the same time. For this next step, I can use the power rule to get this power of 2 to come down to the front. Simultaneously, I can use the product rule to separate this product, x times z, and it'll change this one logarithm to be a sum of logs. So that's using the product rule. All right, so it'll look like this. This 2 is going to come down. So 2 times the natural log of y minus, now you're going to have the natural log of x plus the natural log of z. Now, someone might think that we're done here, but actually there's a sign error on the board. Right here, this is minus all of that. Minus all of that. So it has to be minus all of this. In other words, I'm trying to get you to believe that, or to use parentheses there. So really that subtraction sign has to be distributed. So your final answer is 2 times the natural log of y minus the natural log of x minus the natural log of z. Now we're done. Notice that you have 3 different logarithms and they're all of a single quantity. It's the natural log of just y, the natural log of just x, the natural log of just z. Okay? All right, guys, let's try another one just like this one. All right, this one seems way more involved. We got log base b of a bunch of stuff. X times the square root of y, all divided by z to the 4th power. All of that raised to the 3rd power, or all of that cubed. Okay, what would be the first thing you do here? The first thing I would do in this case is I would bring this power of 3 down. So I would undo this cubing action by using the power rule. So it'll look like this. 3 times the log base b of x times the square root of y over z to the 4th power. So now there's no more power, okay? The next thing I would do is I would undo this division using the quotient rule. Now, just be careful. Everything in the beginning was being raised to the 3rd power. That means everything gets multiplied by 3. So as we break this whole thing apart into multiple logs, don't forget that everything must be multiplied by 3. All right? So, using the quotient rule, we're going to have 3 times log base b of the numerator minus 3 times log base b of the denominator. All right? Notice I put a 3 here, right? Because, again, everything in the beginning was raised to the power of 3. Okay? All right, now, for this first one, I'm going to use the product rule here because this is a product, x times the square root of y. So I'm going to split this up into a sum of logs. For this guy, the only thing I'm going to do is I'm going to bring this 4 down here, okay, down to the front here, okay? Now, it'll look like this. So it'll be 3 times log base b of the first factor plus 3 times log base b of the second factor, the square root of y, okay, minus. Now, if the 4 is going to come down to the front for this last term, don't forget there's a 3 out there already, so it's going to be 3 times 4 log base b of z. Okay? All right, cool. I want to highlight that this one is done, this first term. There's nothing else to do here. And this last one is pretty much done. I'll just have to do 3 times 4, which is 12. But other than that, this one's done. So it's just this one that needs more work. You remember from a previous example that the square root of y really means that y has an exponent of 1/2. So you're going to see me bring down the power of 1/2 here. All right? So it'll be 3 times log of x. You know what? You know what I just realized I forgot? Did anybody else catch it? I forgot my base right here. That's very easy to forget. Don't drop your subscript. Don't drop your base. So 3 times log base b of x plus 3 times 1/2. This 1/2 is that square root symbol, right? As an exponent. That came down. Minus 12 times log base b of z. Cool. Now to wrap this up, it'll be 3 times log base b of x plus 3 times 1/2 is just 3/2. Remember that there's an invisible 1 or an implied 1 that's underneath 3, so you multiply straight across. It's 3 times 1, which is 3, over 1 times 2, which is 2. That's how I got 3/2 there. Excuse me. Log base b of y minus 12 times log base b of z. Okay, everybody? This is the final answer, everybody. Excuse me. All right? It's the sum or difference of logs of a single quantity. Cool. Let's go to example 8, which is the final example. And it has us, before I show it to you, it has us going in the opposite direction. In other words, it gives us something like this. And you have to kind of compile it all back together to get a single log. This example that we just finished doing started off as a single log, and you wrote it as multiple logs. Now they're going to give you multiple logs, and then you write it as a single log. This is how it goes. The example 8 says, rewrite each expression as a single logarithm. All right, here comes the first one. All right, we got 2 times log base 5 of x, 2 times log base 5 of x, minus log base 5 of y plus 4 times log base 5 of z. This looks like the number 41. Should I clean that up a little bit? Maybe, I don't know what would look better here if I put the L closer to there. That's a little better, isn't it? 4 times log base 5 of z. All right, the first thing I recommend doing is to use the power rule to put all of the coefficients back up as powers on the argument. So 2 goes back up as an exponent of 2, and 4 goes back up as an exponent of 4. So something like this. We're going to have log base 5 of now x squared, or x to the power of 2, minus log base 5 of y, plus log base 5 of z, now raised to the 4th power. Okay, that was the power rule. The next thing, I'm going to work left to right, guys. I see a difference. That means these two logarithms can be combined to just one logarithm, a single log, using the quotient rule. Because this is a difference, I'm going to use the quotient rule. That means x squared goes in the numerator of my quotient and y goes in the denominator of my quotient. So something like this. A single log only. My numerator is x squared. My denominator is just y. Okay? I'm going to bring down that last term over here. We didn't do anything to this last term just yet. So I'm going to be a little even more clear, if I may. These two logarithms combined, these two here combined to this one. All right? Now, I see that we have now a sum. That means these two logarithms can be combined using the product rule. Okay? Can be combined using the product rule. So both of these logs will combine to be a single log using the product rule. So it'll be, there's my single log, log base 5 of x squared y times z to the 4th power. Cool, you're done. The only thing I'm going to do here is just clean this up a little bit. You know z to the 4th power really has an invisible or an implied denominator of 1. So we can multiply straight across, right? And so we can write our final answer, maybe a little neater, log base 5 of x squared z to the 4th all over y. That's x squared up there, all right? That looks a little neater there. So you wrote everything as a single logarithm. How did that go for you? Let's do this one more time to wrap it up, all right? Okay, guys, we got 1/2 times log of x plus 1 minus 3 times log of z. Hey, side note, these are common logs, aren't they? How do you know they're common logs? What do we mean by common logs? We mean base 10. How do we know the base is 10? Because the base is not written. Whenever the base is not written, it's assumed to be 10. So these are definitely common logs. Okay, the first thing that I suggest you to do in order to write this as a single logarithm is to take these coefficients, 1/2 and 3, and put them up as powers, okay? So something like this. Log of x plus 1 raised to the power of 1/2 minus log base 10, log of z cubed, like that. You know what I'm going to do, guys, is instead of writing an exponent of 1/2, that's the same thing as a square root, right? The square root, I think, is probably arguably more common notation. Okay, than a fractional exponent. All right, this is a difference. So to wrap this up, we can write all of this as a single log using the quotient rule, right? So this can be written as just one log only. And the first argument is your numerator. And the second argument is your denominator. Like that. So this is rewriting the expression as just a single log. Okay, guys, that's the end of this video, 4.5 properties of logarithms. I'll see you in the next video, which will be a video for 4.6.